Let's start this lesson by generating the data we will train on. This step is not part of the machine learning algorithm. Essentially, we will create fake data with a linear relationship. Once again, we will do that to prove the methodology is working. Feel free to move on to the next lecture if you'd like. In real life, we would normally load the data from some external source, but that's a topic we'll deal with starting from our next section. Alright, if you are still here, we can generate the data. First, I will declare a variable called observations. This variable will contain the size of the dataset we want to generate. Let's work with 1,000 observations. You can do the same with 100,000 or 10 million numbers if you'd like. This choice will affect the speed of the algorithm. When we are done with this example, you can play around with the number of observations. Try 1,000 and then 100,000 and even 10 million. Be careful, as 10 million observations may cause computers to freeze. Alright, we are about to create a two-variable linear model, and the two variables will be called x and z. Let's work on the inputs. We will use the numpy method random.uniform. It draws a random value from a specified interval, where each number has an equal chance of being selected. This method requires three arguments: the lowest point of the interval, the highest point of the interval, and size. The size is actually the shape in which we want to generate the data. Let's choose an interval from -10 to 10. It doesn't matter. Once again, you can play around with these numbers for homework. According to our theory, the appropriate size is the number of observations by the number of variables. So, observations by 1, as we are only talking about one variable, x. We will generate the z's in the same manner. So, these are the two input variables we will feed to the algorithm. Let's combine them in one matrix, called inputs. As theory suggested, the inputs matrix will be of shape the number of observations by the number of variables, or 1,000 by 2. The appropriate method to use is NP column stack. It literally stacks the observations into a matrix. This results in a matrix with dimensions 1,000 by 2. Dimensionality is very important in linear algebra. We can only multiply matrices that are compatible. We want to make sure we can multiply x times w, since our linear model relies on that. In these lectures, I will print the shape of each variable, using the shape method to make sure we are working properly. The appropriate Python method is the object in question .shape. As expected, input is a matrix of size 1,000 by 2, so we have worked properly. Okay. In supervised learning, we must know two major parameters: inputs and targets. We'll also have to generate targets. The weights and the biases are varied through the algorithm, and the outputs are the result from the model employed. We'll leave them to the computer. Okay, since we have only seen the linear model, we will do that in a linear model-friendly way. So, say our targets will be defined by a function f of x and z, which is equal to 2 times x minus 3 times z plus 5 plus some noise. Conceptually, the algorithm must learn this is the function. The weights are 2 and minus 3, and the bias is 5. That's the correct result. If we don't get that at the end, we haven't worked properly. You may be wondering about the noise. It is introduced to randomize our data a bit. Real data always contains noise. It's never perfect. Introducing some small noise will make the data a bit random, yet the underlying linear relationship will be retained. Let's declare the noise variable using the random.uniform method once again. I'll constrain it from -1 to +1, and its size will match the size of the x's and z's. Okay. The target values will be given according to the function we wanted. The proper line of code is targets equals 2 times the x's minus 3 times the z's, plus 5 plus the noise. The targets are a linear combination of two vectors 1,000 by 1, a scalar, and noise 1,000 by 1. Their shape should be 1,000 by 1. Let's check that. Cool. We have our inputs and the desired targets. It is time to create the algorithm.